All right. So we only have just a few weeks left. It's what week is it? It's week 9. It's week 9. Okay. So we got week 9. All right. So we're covering chapter 9 today. Next week is week 10, and we're gonna cover just a little bit of chapter 12, just a few topics from chapter 12. And then I'm going to kind of go back and review stuff from chapters 8 and 9 a little bit more in depth, okay? Because those are important chapters. And then week 11 is going to be a review week. And then week 12 is the final exam week, okay? Yes, question?
On week 11, are we having a quiz?
No quiz on week... oh, wait. Yes. Just a very short quiz, week 11, okay? So yes, we got a quiz. So that was quiz 6, and then you got 7 and 8, 2 more quizzes, okay? And then I'll drop the lowest quiz grade, and I'll do some calculations for you guys so you know what you need to get on the final. If you go into week 10, you can pull up this practice final exam, okay? And I think this is fairly representative of what the final exam will look like, except that it's not multiple choice, whereas the final exam is multiple choice. So you can start to work through this after we cover today's material. You'll have enough to cover almost everything on the final exam except for questions 50 through 52. Okay. So you should be able to kind of answer everything in those questions. This is actually going to be your homework for next week, okay? So your week 10 homework is to work through the practice final exam so that on week 11, which is a review week, we're going to go through it and just kind of make sure we have a good understanding of all of this stuff, okay? So this week is kind of our last heavy chapter. I know last week was pretty heavy, and this week's going to be pretty heavy. So this will be our last heavy chapter. Next week, we'll kind of do just a little bit of chapter 12, which should be fairly lightweight, and then we'll go back and kind of get into chapters 8 and 9 a little bit more in depth. Okay? And then review, and then final exam, and that's it. I won't see you guys anymore, and you'll carry on with your lives, be successful, and do your best there. So anyway, I hope you've enjoyed the course as much as you can. And I appreciate that. I know you guys are trying, and I appreciate that. So and I'm trying my best to make this stuff at least halfway enjoyable. So, all right, let's get into chapter 9 then, okay? Okay, so chapter 8 was all about hypothesis tests, not confidence intervals, hypothesis tests for proportions. Chapter 9 will be hypothesis tests and confidence intervals for means. Okay, so proportions applied to categorical variables. Okay, so if you just think back, chapter 7 and chapter 8, we did hypothesis tests and confidence intervals for proportions. And if you think about it, proportions are for categorical variables. And chapter 9, when you deal with means, okay, so the mean of of a sample. So means are for numeric variables. So if we recall what we covered in Chapter 1, the difference between a numeric variable and a categorical variable, we remember the difference, correct? Yeah? Okay, so that's very important, because when you go through the final exam, it's not going to say, hey guys, this is categorical variable and this over here is a numeric variable, and therefore you're going to be dealing with means, and therefore you're dealing with proportions. It's not going to say that on the final exam. You've got to be able to read the problem and say, oh, this is a numeric variable. It's talking about the weight of animals. That's a numeric variable. Over here, we're talking about, you know, the proportion of people who are left-handed. That's a categorical variable. You've got to be able to read the problem and identify, hey, this is a categorical variable, or this is a numeric variable, and then do the appropriate analysis, okay? Because if you try to do categorical variable analysis when it's numeric variable or vice versa, you're going to get very much the wrong answer, and you will not do well on the final exam. So anyway, I think by this point you should be able to tell the difference between a numeric and categorical variable, but if not, please fix that. Otherwise we'll struggle here, okay? So today I'm going to cover a bunch of stuff, and it feels like a lot, and to some respect it is, but at the same time, the concepts that we've covered for confidence intervals and hypothesis tests, the concepts are exactly the same. The only thing that has changed is some of the formulas. The formulas and maybe a little bit of the steps. Now you're going to be using the t-table rather than the normal z-table. So those things have changed, but the concepts that apply to confidence intervals and the concepts that apply to hypothesis tests, those remain the same. Okay? So I'm going to cover 4 topics today. Okay? We're going to have confidence intervals, for mu. What does mu represent? The mean of what? Of a population, okay? So confidence intervals for mu based on one sample. Okay? And then we've got hypothesis tests for mu based on one sample. Oops, I forgot the word 1 over here. Okay, and then we're going to have confidence intervals and this is mu1 minus mu2 based on 2 samples. And we've got hypothesis tests for, I'm just going to write means with 2 samples. Okay, and so if you recall how confidence intervals worked and how hypothesis tests worked for proportions, those similar concepts still apply today. It's just maybe some of the formulas have changed. Okay, so let's just tackle each of these one by one, and we'll work through a few example problems, and we'll get through all of this. Okay. All right, so let's talk about confidence intervals. For mu based on one sample, okay? And so when we create a confidence interval, what we have is we've got a sample. Well, okay, let's back up. What do we remember about confidence intervals? Okay. That's kind of funny, but also not really if it's halfway true. So as far as confidence intervals go, the idea is what? There's a population that we can't observe, okay? I feel like I'm drawing this picture many times here. We've got some kind of population, right? It's not observed, and you don't have to draw this in your notes. So we've got a population, and what do? We can't observe the population directly, so we take a sample. Based on what we see in the sample, we want to answer questions about the population. Same exact concept here, okay? Whereas when we were talking about proportions, we would look at the sample proportion, and we would make a statement about the population proportion. This time we're going to, if we're going to make a statement about mu, which is the population mean, what do you think we're going to look at over here? The sample mean, okay? So we look at the sample mean. What's the symbol for sample mean? You guys are killing me, man. X bar? We look at the sample mean X bar, and we make statements about the population mean. And what's the symbol for the population mean? Mu, thank you. Okay. P hat, come on. P hat's a sample proportion. Okay, so anyway, so from our sample, we need the following, we need 3 pieces of data, okay? Or 3, I should say 3 numeric summaries. Okay, so we need sample size. What's the symbol for sample size? N. N. The sample mean X bar. I'm not gonna prompt you guys anymore. This is gonna break my heart here. Sample standard deviation. S. Thank you, somebody. Sample size N, sample mean X bar, sample standard deviation S. Okay? And then for our confidence interval, we'll have the following formula. Okay? What do you think goes into the middle of the confidence interval? Okay, all right, let me, so, okay, let's maybe we'll talk, make some fake example, try to help you guys along the way. All right, so let's say we want to know, what is, I don't know, the average weight of a potato, okay? I have no idea, right? Average weight of a potato. All right, and so the true answer, the true value of the average, mu, is unknown. Okay? And the only way to get the true value is we would look at all the potatoes out there. Maybe we specify one species of potato, so like russet potatoes. All right, and what's the average weight of a russet potato that they maybe sell at grocery stores? So the true value would be all the potatoes, and we add them up, and then we divide by how many there are. Right? That's how we would get the true mean. But we don't know that because we can't buy every potato out. We can't corner the potato market. What we're going to do is we're going to take a sample, okay? And so let's say we take a sample of 50 random potatoes, okay? I don't know how we get 50 random potatoes, but somehow we do. Okay, and let's say the average weight of these 50 potatoes, let's say the average weight is 0.42 pounds. Okay? All right. What do you think the average weight of all potatoes is? No. Okay, so my sample has an average weight of 0.42 pounds. Okay? What do you think the average weight of all the potatoes out there will be? Around that, okay? So what value should we put in the middle of our confidence interval? Okay, 0.42, or symbolically that would be our sample mean, x bar. Okay, so this is going to go into the center of our interval, and if that's the center of our interval, what's the next thing that comes in our formula? A plus or minus, right? So in the center is our current estimate. Which is x bar, plus or minus, and then we have plus or minus, it's going to be a critical value, okay, which, because we're dealing with means, we're going to use the t table, okay, so it's going to be called t star. This is called the critical value. And we multiply our critical value by the standard error. Okay? And so what we have over here is that the formula for the standard error is equal to our standard deviation s divided by the square root of n. Okay? All right, what do we call the critical value times the standard error? These two things together, what is this thing called? There, the part that we do plus or minus. Margin of error, great, thank you. I can go home and not cry. All right, so critical value times our standard error is the margin of error, okay? Now, I just want to show the parallels between a confidence interval for mu and a confidence interval for p, okay? So you don't have to write this, okay? But just remember, when we make a confidence interval using p hat, it's p hat plus or minus z star times the standard error, okay? And the standard error was, square root of p hat 1 minus p hat over n, okay? We're not going to bother with that. But what we can see is that in the center, we put our current estimate based on the sample, and then it's plus or minus some critical value times the standard error. Okay, so the parallels are very much there. Okay, so this is the only thing that's changed. X bar plus or minus t star times our standard error. Okay, So from our data, we need 3 pieces of information. So far in our example, we've got the average weight. What's the average weight of a potato? We took a sample of 50 random potatoes. Our average weight was 0.42 pounds. Let's say this is our x bar. We will say 50 is our n, and we need our standard deviation of our sample. Let's say was 0.2 pounds. Okay, I'm just making stuff up. All right, so let's try this out. Okay, so from our data, we have n, we have x bar, and we have s. Okay, so from our data, in the example that I gave you on the potatoes, what is our n? 50. We have 50 potatoes. What's our x bar? 0.42 pounds. That's the average of our sample. And what's our standard deviation? 0.2. Okay. And our formula for a confidence interval is x bar plus or minus t star times our standard error. And we said our standard error is equal to s over the square root of n. Okay? So at this point we can plug in almost all of our numbers, except we've got to figure out what t star is. All right? So how do we get t star? To get t star, yeah, we're going to go to the table, okay? And we need to know 2 things. We need to know what confidence level we want. To get t star, we need the confidence level, and we need something called the degrees of freedom. Okay, degrees of freedom is df, and this is just 1 less than your sample size. So this is n minus 1. So we would have how many degrees of freedom? 50 minus 1, we would have 49 degrees of freedom. So our degrees of freedom is equal to 50 minus 1, which is 49 degrees of freedom. Okay? Now, there's when we go to our table, let's say we want to do confidence level. Let's say I want to make a 95% confidence interval. Okay? So we're going to go to our reference table here. Okay, and we're going to go to this column that says confidence level 95%. And we're going to go down this column until we get to 49 degrees of freedom. Okay? Now what we see is that we don't have actually 49 degrees of freedom. So this leftmost column is the degrees of freedom. And we've got 50 degrees of freedom, and we've got 40 degrees of freedom. Okay? So the true value is going to be somewhere in between here. And our kind of the philosophy to stay on the safe side is we always round down. Okay, so 49 is closer to 50 than it is to 40, but to be safe, we're always going to round down and use 40 degrees of freedom. Okay, so we cannot find 49 degrees of freedom, so 49 df is not on the table. Okay, so we will always round down. And we will use 40 degrees of freedom, okay? Even though 50 degrees of freedom is closer, just to be safe, we're going to use only 40, okay? So it's like, let's say you have a room and there's 49 seats, okay? Should you send out 50 invitations or 40 invitations, okay? Just to be safe, we're going to send out 40. In case they all show up, all right? I know that's a silly example, but that's what we do, okay? All right, so we're going to use 40 degrees of freedom. So the t star at our table is going to be 2.021, Okay, so our t star (2.021). Okay, so let's plug all of these values in. Okay, so we've got x bar plus or minus t star times our standard error. Okay, our standard error is s over the square root of n. Okay, so our standard error is going to be 0.2 divided by the square root of 50. Okay, I got 0.02828. Okay, so my x bar is 0.42 plus or minus 2.021 times my standard error of 0.02828. Okay, so I've got this. I'm going to multiply this by 2.021, and I get 0.0571. So I have 0.42 plus or minus 0.05716. So I'm just going to leave it at 0.057. Okay. So to get my lower and upper bounds, what do? I do 0.42 minus 0.057, and I get 0.363. And on the upper bound, I do this plus 0.057, and I get 0.477. Is this okay with everybody? Okay. All right, so let's just answer some questions or make some statements here. I would then say stuff like, I am 95% confident that what? I'm 95% confident that the average weight of potatoes in the population, so basically all potatoes out there, all right? So I'm 95% confident that the average weight of potatoes in the population is between 0.363 pounds and 0.477 pounds. Okay. So then, here's a question. Someone asks, do we have evidence that the average weight of all potatoes is different from 0.5 pounds? Okay. And then we'll ask the same question, do we have evidence that the average weight of different potatoes is different from something else? Let's say 0.4 pounds. Okay. What is the answer to our first question? The answer is yes. And why is our answer yes? Yeah, because 0.5 pounds is outside of our confidence interval, right? So 0.5 pounds is outside our CI. So we have evidence that the mean weight is different from 0.5. Could the actual mean weight be 0.5 pounds? Yes, no, maybe? The answer is yes, it could be 0.5 pounds. What does it mean if the mean weight was actually, mean weight of all potatoes was 0.5 pounds, okay? So remember, our confidence interval is based on a random sample, okay? And so if the mean weight actually is 0.5 pounds, then that means because of random sampling, we happen to get this weird sample that makes us believe that the mean weight is over here, but in reality the mean weight was over here, okay? Maybe I'll write that down here, okay? On the other hand, do we have evidence that the average weight of all potatoes is different from 0.4 pounds? The answer here is no, okay? 0.4 pounds is within the interval. Okay, so it is a plausible value. For mu, the mean weight of all potatoes. Okay, does this mean that the mean weight is 0.4 pounds? No, okay? On the other hand, you know, this does not prove that the mean weight is 0.4 pounds. Okay? It's just 0.4 is a plausible value, but it doesn't necessarily have to be 0.4 pounds. Okay? So and over here we have evidence that it's different from 0.5, but theoretically it is possible that the mean weight is 0.5 and we happen to get a weird random sample. I'm hoping these statements about confidence intervals does not seem too far-fetched compared to the statements we made about proportions. Okay? Reasonably similar. Okay? It's just the formula has changed. Okay? And the way we get our T star, we have a table of values. Okay? Whereas, how do we get critical values Z star for confidence intervals with proportions? Z star, what do we do? I said there were just 4 values you needed to know, right? 95% was 1.96, 90% was 1.645. I gave you those 4 values, and I said those are the 4 values that you need to know for Z star, okay? Over here for T star, you got a table of values that you look up. Okay? I'm going to go on to our next topic then. And that will be hypothesis tests. For mu based on one sample. Okay? So with hypothesis tests, again, we have questions about the population, and we ask, you know, does our data provide evidence that the population looks like this, okay? So we always start off with our hypotheses, right? Okay? So our null hypothesis is always going to be mu is equal to some number. I'm going to just make up a number here, like 25, okay? You know, this number that we put here, this is known as mu sub 0, okay? So our null hypothesis is always mu is equal to some value, mu sub 0, okay? But you just have to remember mu sub 0 is this is just some number. Okay, like 25. Okay, and then the alternative hypothesis will be things like mu is not equal to 25. Or, what else might we see? Mu is greater than 25. or mu is less than 25, okay? And again, you know, symbolically, the generic form would be mu is not equal to mu sub 0, or mu is greater than mu sub 0, or mu is less than mu sub 0. Okay, but again, mu sub 0 is just some number, okay? And this some number comes from the statement of the hypothesis, or statement of the question. And just like when we were dealing with proportions, you know, it will ask things like, do we have evidence that the mean is less than 25? Or do we have evidence that the mean is different from 25? Or something like that, okay? So read the question, you know. Read the question to decide what your hypotheses should be. Okay, look for keywords like different, you know, this larger, smaller, etc. to help decide what symbol to use in the alternative hypothesis. Okay. So this part is exactly the same as for proportions, except instead of mu, we're using p, right? Okay. And likewise, when we were dealing with proportions, I said never use what in the null hypothesis? Never use p hat, right? So over here, you would never use x bar, okay? So never use x bar in the hypotheses. Okay? And still applies. Never use p hat in the hypotheses either. Okay? So your hypotheses will always be about mu if you're dealing with means. Your hypotheses will always be about p when you're dealing with proportions. You'll never have x bar, you'll never have p hat in your hypotheses. Null hypothesis always has what sign in it? An equal sign. Your null hypothesis will always have an equal sign somewhere in there. Okay, so once you have your hypotheses established, we'll do our preparation step. Okay, so the preparation, we have our significance level alpha, okay, with you know, default value of 0.05. So if alpha is not specified in the problem, assume that it's 0.05. Otherwise, use the alpha that the problem specifies. Okay, and then your data. So label your data. Okay, we need to have n, our sample size. We need to have x bar, our sample mean. And we need to have S, our sample standard deviation. All right, and then as far as calculations go, our standard error is the same as the standard error that we used for the confidence intervals, S over the square root of n. And our test statistic, T, okay. So over here, whenever you're dealing with means, you're always going to be using the T table, okay? When you're dealing with proportions, you're always using the Z table, okay? So the proportions, our test statistic was Z. when we're dealing with means, our test statistic is t, okay? And our test statistic t is going to be x bar minus mu sub 0 divided by our standard error. Okay. And yes, question.
What does that S for again? On the standard error?
S is our sample standard deviation here. Okay? Okay, so this is your calculations. All right, the way we get our p-value, though, is very different. Okay, so this part is going to feel just a little bit strange at first. Okay, you know, if you have a computer or a fancy calculator, it'll spit out a p-value. Okay, but we're going to be using these tables, and so the way we get p-values from the table is different from the way we use the z-table. Okay, so basically, when you do your calculations, you get your standard error, you get your test statistic, and then once you have your test statistic, t, you look that up in your table to get your p-value. Okay, so then you, whoops, hold on. So the next step will be to look up t in the table to get a p-value. Okay. So I'm gonna I'll cover this step on the next slide. Okay. But then once you get your p-value, we can do our interpretations and our conclusion. Okay. And the thought process here is exactly the same as it is for proportions. Okay. And so if our p-value is greater than our significance level alpha, what is the decision we make? If the p-value is larger than alpha, we say, yeah, we do not reject the null hypothesis. Okay, and we would say something like, you know, we do not have evidence that blah, 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 blah. Whatever, you know, basically is whatever appears in the alternative hypothesis, okay? Okay, and on the other hand, if our p-value is less than alpha, we reject the null hypothesis, and we say we do have evidence that blah, 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 basically that the alternative hypothesis is true. So this is what we have. Okay, so I'm hoping this also feels familiar based on what we saw in chapter 8. Okay, so the only thing that has changed is the way we calculate our standard error and the way we get our test statistic. Okay, and then so finally, the way we look up the t to get a p-value is, I would say this is significantly different, and so we'll cover this in detail. But before I go there, I just want to make sure all of this stuff is feeling okay. All right, so I got some head nods and I got some smiles, so it's a good thing. Okay, so the way we look up our test statistic t in the t table is, so let's say we have n equal to 22. So we have a sample size of 22, and after all of our work, and you know, after calculations, our test statistic t is equal to 2.14. Okay? So let's say our test statistic t ends up being 2.14, and we have a sample size of 22. Okay, what do we do? To get our p-value, to go from t to p-value, okay, well, I'm sorry? So this is going to depend on our alternative hypothesis, okay? So if our alternative hypothesis is greater than or less than or not equal to, this is going to affect what we do, okay? So if the alternative has a greater than sign or a less than sign, we have a one-tail test. And if the alternative has a not equal sign, we have a two-tailed test. Okay, so what we're going to do is we're going to look up t is equal to 2.14. And what we have is we've got n is equal to 22. So what will our degrees of freedom be? 21. And degrees of freedom is n minus 1, so that gives us degrees of freedom equal to 21. Okay? So what we're going to do is we're going to go to our table, and we're going to go to this row for 21 degrees of freedom. Okay? So you go to your table, you look up the row for 21 degrees of freedom. Can you guys see this? And we're going to say, okay, my t was 2.14. So I want to say, where does 2.14 fit in this row? Okay, so 2.14 fits in between these two numbers. Okay, it's bigger than 2.08, it's smaller than 2.518. Is that okay? Yeah. All right, so maybe I'll copy this. So what we have is we've got 2.14 is in between these two numbers. Okay. Something's going on here. Oh, my thing's crashing. Okay, cancel. And what we're going to do then is we're going to go to the top of the table. And we're going to say, okay, well, if our value is in between these two columns, then our corresponding tail area will be in between our column headings, okay? So we went in between, so we said 2.14 is in between here and here, and this means our corresponding tail heading, the tail area, is going to be in between 0.025 and 0.010. Question? So 21, our degrees of freedom is n minus 1. Okay? Okay? All right, and so we have 2.14 is in between these two things. So what we have is we say our tail area, the tail that corresponds to this, is in between 0.025 and 0.010. So our tail is between 0.025 and 0.010. Okay. All right, so this is, 2.5% basically, and this is 1% basically, okay? Okay, we didn't really specify anything, okay? So if we have a one-tail test, our tail area is our p-value, okay? So if it's, for one-tail test, the tail is equal to our p-value. So this means my p-value is between 0.025, and 0.010. I'm going to shrink this down here because it's a little bit. So I get my tail area is between, I'm sorry, my p-value is between 0.025 and 0.010, okay? I can shorthand this and say my p-value is less than what? 0.025, but at the same time is greater than 0.010. Okay, so to say the p-value is between 0.025 and 0.010 is exactly the same as saying my p-value is less than 0.025 and at the same time my p-value is greater than 0.010. This is okay? So that's a one-tail test. Okay? If we have a two-tail test, what do? Yeah, we just multiply these numbers by 2 and we say our p-value is between our double the tail area. Okay? So what we have is our tail area is between 0.025 and 0.010. Basically, I'm going to say my p-value is between not 0.025 and 0.010, but between 2 times 0.025 and 2 times 0.010. Okay? So this becomes 5% and this becomes 2%. So I would say my p-value is between 5% and 2%. Or shorthand, I would say 0.02 is less than my p-value, which is at the same time less than 5%. Is that okay? So some of us have it, but I want to make sure the rest of us have it. Okay. Yeah, so that's our answer. So to go from a test statistic t to a p-value, this is what we do. Okay. So a lot of times you're not gonna, when we had the z table, I just said round off to 2 decimal places, and then you kind of got an exact value for your p-value. Okay. Over here, you're rarely going to get an exact value. Only when you get one of these numbers exactly will you get an exact value for your p-value. But otherwise, it's almost always going to be in between a range. Yes?
So in this instance where we have 0.05, that's equal to our alpha?
Mm-hmm. So,
what would we say that?
So but notice our p-value, it's not less than or equal to 0.05. It's less than 0.05, okay? So if our alpha was 5% and we said our p-value is between 2% and 5%, our p-value is still less than 5%, okay? Because the only time you would get p-value equal to 5% is if your test statistic t ended up exactly at 2.080 and you doubled it, or if your test statistic t ended up exactly at 1.721. Otherwise, it's going to be a little bit less than that or a little bit more than that. Okay, and we might not know exactly how much it is, but that's okay. We just need to know, is it bigger than 5% or is it less than 5%? And this tells us, hey, your answer, your p-value, it's less than 5%. We don't know how much less, but we do know it's less. Okay, so a few other pointers here. Okay, so if your test statistic t is negative, okay, just ignore the negative sign and proceed. Okay, because the t table is symmetric. Okay, it's symmetric around the axis, and just ignore the negative. And proceed. I guess there is a few things. Okay, there. if your alternative hypothesis has a less than sign, then t should be negative. And if the alternative has a greater than sign, then t should be positive. Okay, and if these are not true, we have what we call a directionality problem, which I don't feel like covering in this class. Okay, all right, but it exists, and it is something that you have to kind of watch out for. But as far as the scope of this class, I'm going to kind of just ignore the problems with directionality. I would say it's a little bit more on the rare side, but basically, if these are violated, okay, we have what we call a directionality problem. Okay. All right. So if your test statistic t is negative, ignore the negative and proceed. Okay. There's a few things. I'm going to just copy kind of the first few rows here to just kind of illustrate what's going on here. So what to do with extreme t values. Okay. So, if t ends up like a big number, if, let's say if t is equal to 400, okay, then 400 goes over here, right? T if equals 400 ends up over here. And so this means your tail area, is it going to be more or less than 0.001? It's going to be less than 0.001, okay? Because what happens with the tail area is it starts off large over here and it gets smaller over here. So if your t ends up being huge, then your tail is going to be much less, okay? And on the other hand, if your t ends up being small, so t is equal to 0.0 or 0.2 or something like that, then that means the corresponding tail is greater than 0.100. Okay. So, because if we think about this, it makes sense. Okay. 0 is in the middle. If I draw t very close to 0, how much do I have in the tail? I have a lot. Okay. On the other hand, if so this is t small, corresponds to big tail area. On the other hand, if I've got 0 over here, and t ends up being way out here, t large, then my tail area is small. Okay? So that's things to keep in mind. And so sometimes, in the last problem we said t is between, our tail area is between 2.5% and 1%. Okay? Sometimes you just say, I don't know exactly what my tail area is, but I do know it's less than 0.001. Or I don't know exactly what my tail area is, but I do know it's more than 10%. Okay? And that's fine. We don't need to have exact values all the time. Is that okay? All right, well, let's pause here. We'll take a break. We'll do an example, and then we'll cover the other two topics as well.